The topic is surface wetting and its modification. So first of all, what is the surface? Surface is the topmost layer of any material that is in contact with another uh, phase. For example, solid materials have their surface, but for the liquids, interface is used. So this term interface is actually every surface or the boundary between two type of materials like liquid air or solid air. So the surface term is only used for the liquids or the solids which are in contact with the air. So briefly we can say that the interface is a generalized term which is used to express the boundary between two materials, and the interface which is existing between the solid or liquid versus gas is known as surface. So here we are going to discuss the surface wetting. So surface wetting is the displacement of one fluid from another fluid, and from a surface is known as wetting. And in wetting, three phases are involved. For example, if we pour a liquid at any surface that is solid, it displaces the air. So this displacement is known as wetting. So simply we can say that the displacement of air by liquid from solid or liquid surfaces is wetting. And the ability of a surface to get wet easily is known as wettability. For the experimental determination of the wettability, a term is used known as spreading. So let's take an example. Here we have a substrate which is solid, and a liquid is placed over the surface of this solid substrate that is spreading to a length of a to b. So in this scenario we have three phases, that is solid, liquid and air, and each phase have a surface with specific values of surface tensions. So here what is the surface tension? It's the tendency of a liquid surface to shrink into the minimum surface area possible, or it is the property of a surface that display a similar phenomena that is like a stretched elastic membrane of the surface. Surface tension is represented by a symbol known as gamma. So here we have three types of surface tensions. This one is the surface tension between solid and air. This one is between solid and the liquid, and the third one is between air and liquid. So here wetting phenomena is studied at the surface of substrate, and the liquid will move and spread at the surface of this substrate. So here we can divide the interfacial surface tension into two types, that is before spreading and after spreading. Before spreading, the solid surface was exposed to air, so the before spreading surface tension was only solid and air. And after spreading we got two type of interfacial surface tensions, that is a form of energy, and the unit is dynes per centimeter. So here we have a surface tension value of, that is for liquid air and the liquid solid surface. So here we have an initial and final state. So for the change in free energy should be negative for the spreading. As we know that the surface tension of solids is far much higher than the surface tension for the liquids and the liquid air interfaces. So here we can see that the overall surface tension of the solid is decreased. It means that the change in energy for this process is decreased. So the delta G is negative, whereas for the formation of new interfaces, the change in Gibbs free energy is positive. So the total decrease in free energy per unit area before and after spreading is calculated using formula given here. Here delta G is Gibbs free energy over the area, and that is the difference between the surface tension before spreading minus surface tensions after spreading. So in order to increase the spreading, we must add the substances which can increase the wettability. So there is a coefficient that is used to measure the extent of wettability is known as spreading coefficient. It is the driving force for spreading of a liquid at a surface of a solid. So spreading coefficient for the liquid and solid surface is equal to the surface tension difference in the surface tension, that is again before and after spreading. So here we have two equations. First one is describing the Gibbs free energy change for the spreading phenomena, whereas the second one is describing the spreading coefficient for the systems we have. If the spreading coefficient is positive, it means that the surface tension that is actually the sum of the surface tensions developed after spreading must be lower than the value of surface tension that is existing before, whereas if the value of the spreading coefficient is positive, then the Gibbs free energy value will be negative. So the value of free energy is negative, exhibit the possible spontaneous spreading, whereas the negative value of spreading coefficient gives the value of negative free energy, that is from the equation number 1. So this will predict the non-spontaneous spreading. So for this kind of spreading we need to do work. Now take an other example where we have first surface is liquid, that is an liquid air interface, which is then displaced by another liquid. So if we have two liquids, L2 is spread over the surface of L1, the spreading coefficient is equal to the, from this figure we can see that here we have liquid L1 which is in contact with air. So L1 have a surface, that is L1A. This is the surface tension. So if we displace the air with another liquid, that is L2, so we get surface, that is L2A, and an interface, that is L1 L2. So for this system, spreading coefficient, that is the spreading between L1 and L2, will be written as the surface tension before spreading, that is the actually L1A, and that is subtracted by the surface tensions obtained after the spreading, that is the surface tension for the liquid 2 and air, and the interfacial tension, that is between L2 and L1. For this case, again, if we have the surface tension value for L2A For higher surface tension of L1A as compared to the sum of the surface tensions obtained after spreading, the overall spreading coefficient will be positive. That will lead to the negative Gibbs free energy. So let's discuss an example of the spreading. Here benzene is spread over the water surface. Initially it will spread over the water, but after some time lenses will be appeared due to retardation. So in this case, initially spreading coefficient, that is between liquid 1 and liquid 2, is positive, so it's spreading over the surface. So initially the surface tension for measured for the water, that is the liquid 1, is 72.8 dynes per centimeter at 20 degrees centigrade, and the surface tension for the benzene is 28.9 dynes per centimeter. And the calculated value of interfacial tension is 35 dynes per centimeter. So overall spreading coefficient is 8.9 dynes per centimeter. That is the positive one. It means that the spreading is observed initially. But after certain duration, benzene is saturated with water, and for this system, again surface tensions of the uh, mm, different interfaces were measured, leading to a negative value of spreading coefficient that will give the positive Gibbs free energy change for overall spreading. So this is the reason, that's why the spreading has changed to retardation. It means the formation of lenses was observed, and the similar phenomena was observed for an hexanol, which exhibit the similar behavior.